Okay, so in this video, we're going to be talking about chapters 4, 5, and 6 from the book. And we're actually transitioning now from um, the first part, of course, when we talked about descriptive analytics, where we basically take a set of data and develop a set of metrics around it that describes it, to predictive analytics. All right, so for as an opening here, we're going to talk a little bit about probability, right, basic probability. Um, the focus of our efforts is not really on doing an in-depth analysis of probability. You can take a statistics class and actually spend the better part of a semester focused on probability, the different concepts and different applications of probability. For our purposes, we're just going to talk about some of the basics. All right, and kind of to keep the other stuff, forego the other stuff. All right, the important things to be a couple of things to remember. Obviously, probability is basically some estimation of an event, the possibility of an unknown event occurring in the future. All right, given this particular set of circumstances. Um, so we're going to talk about basic probabilities, and then some of the applications of this, are kind of our introduction into predictive analytics. All right, which is in chapter 5 and chapter 6. All right, so for starters, the objective of this chapter is really to understand the basic probability concepts. All right, so probability, a little definition, um, refers to the relative chance that an event will occur. All right. It's really what we're trying to do is trying to do some sort of approach to measure and quantify uncertainty. Right? Will event, what is the likelihood that something might occur? All right, and probability is always measured between 0 and 1. And if I have a series of events, the probability of an event will always, the sum of all of the individual probabilities will add up to 1. All right, so if something is like flipping a coin, for example, uh, chance if we flip a coin one time, the probability of us getting ahead is 50-50, right? Because it's like two choices on any individual flip. So basically, that would be 0.5, all right, which is obviously between 0 and 1. And the probability that it would not be say a heads, would also be 0.5. Or add the two together, they add up to 1. All right. So there's a couple different types of probability, a couple different approaches. Uh, we're looking at trying to assess the probability of a specific uncertain event. Um, the first one is something we call a priori. Right, and it's based upon prior knowledge of the process. All right, so basically, what it will be is we know the total number of outcomes, of possible outcomes, and we know the number of ways in which a particular of those total outcomes, a particular event can occur. So what we do is we divide the number of outcomes into the number of events, and that comes up, and we get a percentage, which we say is the probability of occurrence. All right. Empirical probabilities, we calculate it really the same way, but we structure it a little bit differently. All right, empirical, and we'll take a look at we'll look at it at the example of like an empirical um, calculation of a probability. All right. Subjective probability, which is the third type, it's based on a combination of an individual past experiences, personal opinion, and analysis of a particular situation. So the likelihood of an event is based upon what we believe to be true based upon past experience. Like we think that it'll be a 50% chance or 70% chance of something occurring because we've experienced this multiple times, and it would appear that 70% of the time something like this would happen. All right, so these are the three types. All right, so we're looking at a priori. All right, which is, as we said, is the based upon prior knowledge of the process. We'll use an example here. In this case, we'll use take a deck of playing cards. All right, so 52 cards in total. All right, 50% of them are red, 50% of them are black, and then 25 of them can also be described as being in a different suit. So basically, it's was it diamonds, hearts are red, and clubs and spades are black. All right, so that would be there would be 25% of each one would be if you were going to look at a heart or a spade or whatever. Okay, so we'll look at this. So given our deck of 52 cards, all right, we would say that the probability of getting a red card would be the total of 52 divided into the number of red cards, which is 26, right, which is 50%, right? Which is kind of what we had said, 50%. There's 26 red cards out of 52. So if we draw a card with 50% chance, right? Very simple. Empirical is a little bit different. Differently. Actually, what we do is we will do a population. What we'll do is we'll construct a table of probability. So if this looks familiar, this is actually what we had seen previously with but apply. In this case, what we're going to do is we're going to use this to create a probability. We're going to do a calculation of this to estimate probabilities. All right. So in this case, what we have is a total population of 439 students, some of which are male, some of which are female. So the total number of male students is 229, female is 210. And then also another characteristic is either going to be taking stats or not taking stats. In that case, we have 160 not taking stats and 279 who are not. All right, so this looks, and what we would do is to figure out what the probability of a male taking stats, all right, is what we would do is we would basically divide the total population of 439 into 84, which gives us 0.191, which is our probability, about approximately 20%. All right. So, as I said, this looks familiar because basically this is similar to what we had looked at in the previous chapter. What we'll have is we have row calculations, we have column calculations, and we have total calculations. All right. So this is really the same thing, except that what we're doing is we're applying it in terms of a probability of an event occurring. All right. So a little bit more terminology. Each possible outcome of a variable is called an event. All right. So we can look at events in a couple different ways. If we take an event described by a single characteristic, so in this case we would say a red card would be an example of that. We would call that a simple event. All right. And that's to be compared against what we call a joint event, in which we're looking at two or more characteristics. All right. So in this case, it would be a red ace, or a black jack. Basically, we would have two characteristics. One would be the color of the card. The second one would be the face of the card. All right. And the other thing to remember about these probabilities, or when we calculate the probabilities, the complement of that is basically that number 1 minus the 1 minus the probability we calculate. All right, because what it is, everything adds up to 1. So if it's 50%, it's 1. It would be 1 minus 0.5, which is also 0.5. All right, or as we look at this, that's what we call. So that's a complement. So once again, everything adds up to 1 when we take all of these percentages. And we can use that as a check. All right. So in this case, when we talk about sample space, so our sample space is what are all of the possible events we could get from, collection of all the possible events. That is our sample space. So in this case, it's all 52 decks of 52 cards that we have within the deck. Right. So what we're going to do is we're going to do a simple probability, all right, which is the probability of a simple event, basically one characteristic. So in this case, what we'll do is we will have a either red or non-red in this case, or the probability of an ace or non-ace. All right. So in this case, if we add up our numbers here, we have 26, 26, 4, 48, which is 52. Right? So all the numbers add up. So what we will do is we want to get the probability of an ace is 4 divided by 52. And the probability of a red card, all right, would be 26 divided by 52. So you see, it's similar to what we had, the same calculations we had done before with the, where we had calculated the row, the column, and the total percentages for each of the values of the variables that we collect. Right. So that's simple probability. Joint probability, as we said, refers to a probability of an occurrence of 2 or more events. So in this case, as we described it, it would be the probability of a red ace would be a considered a joint probability. And we can use, once again, we can use our table. We can use our construct here to enable us to do the calculations, or figure out our calculations for what we want to for our calculation of the probability. In this case, if we're looking for a red ace would be the intersection between red and ace. All right, and we simply divide that by our total population, which is 52. That would be the probability of a red ace. Probability of a non-red ace would be of a similar, a similar kind of calculation. Or we could take it as the inverse. We could take it as the inverse of that. All right. So conditional probability. So that's a joint probability. All right, of 2 or more events. A little bit of a difference of this is what we call a conditional probability. All right, whereas a joint probability is probability of 2 or more events, or 2 different characteristics. A conditional probability is the probability of one event occurring given that another event has already occurred. All right, so what would be the probability of a red card given that we've already have drawn an ace? All right, which is 2 out of 4. Or an ace that if we know we've drawn or we got an ace, what's the probability that is also a red card? Or if we've already drawn a red card, what is the probability of that card being an ace? All right, so it's a little bit of a little bit of a different flavor of as opposed to joint. So conditional is, okay, given that we have 2 characteristics. If we have one characteristic, what's the probability of us getting the other one? And once again, we can look at our table here, and we can, by taking the appropriate values from within the table, we can calculate these percentages very simply. All right. So once again, We said both the joint and conditional probabilities look suspiciously like our contingency tables, right, where we calculate the total percentage, the row percentage, and the column percentage, right? So really, that's all we're going to talk about for probability. Right? So given that, so those using that basic information, what we're going to do is let's take a look at Chapter 5. In Chapter 5, what we've talked about in Chapter 5 is probability distributions. All right, so probability distribution is, if we look at a formal, if we want to look at our formal definition here, we're going to talk about what we're going to talk about in this chapter is what is a probability distribution, what are its properties, and how to compute something we're calling the expected value and the variance of a probability distribution. All right. So, a couple things. We have some terminology or some definitions here. So, first thing we have is something called a random variable. Random variable is a variable that varies in value purely by chance. It represents some type of a possible numeric value from some uncertain event. All right, something will happen. We can get any possible numbers within a particular range or specification we can get. All right, so that's a random variable. And we have a couple different types of random variables. So one is something we call discrete variables. All right, so a discrete variable produce outcomes that come from a counting process. So basically the number of classes, we'll use an example, number of classes we're taking, or if you're counting something. All right, and then continuous variables, are derived from taking some type of measurement. So, you like a salary or weight or age. Those would be considered, measurements. So those are going to be called continuous variables. All right, and Chapter 5 we're going to talk about Chapter 5. We're going to talk about the discrete variables, and in Chapter 6 we're going to talk about continuous variables. All right, and how these work in terms of our probability distributions. All right, so here's another kind of key definition here. So a probability distribution for a discrete random variable is a listing of all of the possible numerical outcomes for that variable, as well as the probability of occurrence associated with each outcome. All right, so we have, so basically we have a some number we've collected. All right, and we're going to apply it against a something that's going to have a stack of possible numerical outcomes. Right, so with a variable we can have x number of or n number of outcomes, and each of those outcomes will have a probability associated with each one. All right. So what we do is we call that a probability distribution. All right, and we have ways we handle it from a discrete perspective, and we also have ones we use from a continuous. All right, so let's look at the discrete in a little bit more detail. So we'll say, so a good example of discrete is tosses of a coin. Right? There's no measurement involved. It's simply you toss a coin, it's an event. So we're going to say x is going to be equal to the number of heads and two tosses of a coin. So what we'll do is we will do we have all of our outcomes, which is x. And then we have a probability distribution associated with that of the occurrences of, if we say it's the number of heads and two tosses, what we will have is, we will have either no heads at all, probability of one head, occurring in the two tosses, or the probability of two heads occurring in those two tosses. All right. So this is kind of the distribution of these events, these discrete events. So the probability of having a zero, of having no heads, is 25%. All right. Um, the probability of getting at least one head on both tries is 50%. And then finally, the probability of getting two heads in two tosses of the coin is 0.25. We add those up. We have a total probability, our total distribution is 1.0. All right. So we can represent this in a graph. All right. So on the y-axis, we can list the probabilities of occurrence, and on the x-axis we can list the outcomes. All right, 0, 1, or 2. All right, and this is the probability. So if this is x, if x is this outcome, the probabilities are shown here. All right. So this actually goes back. If one of the things that probability distributions share with what we've been talking about is this idea of central value. Right? So the idea of, we talked about central value, the mean, that data, when we're looking at descriptions of data, there is a tendency of the data to collect around some form of central value we call the mean. All right. So one thing what we'll do is we will calculate the mean of something, and then what we'll do is we will calculate the distribution of everything around that mean. All right. What is the deviation? What's our standard? What's our variance? What's our standard deviation? If you remember what we talked about before, with probability distributions, we have the exact same thing, except that we call it something different. So in probability distributions, we call this stuff expected values. All right. And we get the expected value in kind of a similar fashion, except that what we'll do is the way we'll calculate that will be we will multiply the probability times the outcomes. So it's 0 times 0.25 plus 1 times 0.50 plus 2 plus 0.25, which adds up to 1. All right. So this is the mean. So, and the idea is the expected value is just simply the mean of the probability distribution. All right. And in addition, we can also calculate the variance and the standard deviation. Now we'll see where the applications of this. We'll see more. We're going to talk a little bit more about it when we look around continuous. All right, but just for right now, it suffices to know that our mean, our expected value is the mean of the probability distribution, and we could also have a corresponding variance and standard deviation for that, which actually gets calculated very much the same way as same basic formulas for variance and standard deviations. Right? And what it does is both of these are measuring the distribution of values around some sort of central value. In this case, we call it an expected value. So in this case, we take our probability distribution here. We run through the calculation. All right. And what we find is the variance is 0.5. If we take the square root of 0.5, we'll find it as 0.707, which is the standard deviation. All right. So our mean is 1, and our standard deviation is, point 0.707. Now we can use this, in a couple different ways, but like one way we can do it, we can use this as a means of doing a risk assessment. So we'll use the case where we have two investments. All right, investment, E or investment A, investment B. Both have a expected value. Both have a standard deviation. All right, and what we want to do, we want to select an investment that yields the highest expected return and the lowest risk. All right. So in this case, what we'll do is we'll put together our table. All right. Which is what we're saying is we have three, we're going to evaluate investment outcomes against economic conditions. We have two types of investments, and we have three potential economic conditions. So we have a recession, a stable economy, and an expanding economy. All right. So we have the standard, and then for each one of these, what we would have is we would estimate in a recession that we would lose $25 in our investment if we were in a recession, but we would lose $200 if we were in the aggressive fund. In a stable economy, we'll make 50, and for the aggressive fund, we would make 260. In expanding economy, we would make 100 for the passive fund. We would make 350 in the aggressive funds. All right. So what we can do is we can calculate the expected value, the mean of these, for our outcomes here, for both of these, and we can also calculate the standard deviation. All right. So the standard deviation, as we said, is basically an estimate of how the data is spread. So what we would have would be expected value of 50, all right, with the deviation of plus or minus 43. All right. That would be for the passive fund. So we would get, we would likely make money on it, but we may or may not necessarily make a lot of money. All right. Whereas with the expected value, now I'm going to I could potentially make almost double. But the variance, as we can see here, is much higher. All right. So our range of potential values, basically our standard deviation coming off of that, is pretty wide, is very wide, as a matter of fact. All right. So as we can see here, that in this case, the expected value is greater than the standard deviation. In this case, the standard deviation is greater than the expected value. All right. So the decision. So what decision would we take? Well, it really depends. Looking at these economic conditions, what do we think about? Because what's going to happen is the economic conditions, whatever the outcome of the economic conditions, will really drive how the investments will go. We're putting a probability of 0.2, 0.5, and 0.3. It's really a matter of how strongly do we feel that this is an accurate representation. All right. Which will determine which one would be, this one, if we wanted to put it into an aggressive fund, we're saying right now it's 0.3. So what if this was, say, recession 0.1 and expanding economy would be 0.4? Well, then I would feel more strongly that this would be a good choice. What if we said, though, we flip this around and we say we make the recession, say we make the expanding economy 0.1 and the recession, say, 0.4? Well, then maybe we would want to, weigh the expected, look at our value here around the passive fund. and take a more conservative approach. All right. So it's so this is just kind of an example of how we can compare. Basically what we're going to do is we're going to calculate the expected value or the mean of the probability distribution and calculate the standard deviation of the probability distribution and then use that as an estimate to be able to make an informed decision. All right. So there's a couple different types of probability distributions. So what we've been talking about is really the discrete probability distribution. So there's a couple specific types of these we see in the discrete world. One is called binomial. The other one is Poisson. So binomial, one of these is dealing with a universe or a testing environment in which we have a fixed number of tests we're going to run, which I believe is the binomial. And the Poisson assumes there's no limit on the number of tests, so it's like a continuous flow of tests generating discrete values. All right, so those are this. So that's a description of our discrete probability distributions. Now we're going to talk about continuous. This is chapter 6. And when we talk about continuous probability distributions, now we're going to talk about our friend, the normal distribution. All right, so let's take a look at that. So the normal distribution. So we've talked about this. We're going to talk about what we talk about in 6 is going to be compute probabilities from the normal distribution, and then how to use this normal distribution to solve problems. So, definition: a continuous variable is a variable that can assume any value in a continuum. All right, so there's a whole variety of outcomes, and there's no way of predicting what that outcome would be. So theoretically it could assume any value. All right, and the normal distribution, as we call it, is a bell-shaped curve with a mean and a normal distribution. The mean is equal to the median, which is equal to the mode. This is the central value, all right, around which all of the data is clustered. And what happens is 1/2 of the data is to the left and 1/2 of the data is to the right. All right, so the mean, median, and mode, all these are equal. Location of this, of how this curve is structured, is determined by the mean. And then the spread of the data is determined by what we call the standard deviation. All right, so it's a combination of both of these, and basically the universe of the outcomes that we're looking to draw fall underneath this curve. So this curve represents all of the possible outcomes. All right, and the random variable, as we say here, has an infinite theoretical range of plus to minus infinity. All right. So as we're looking at this, so the normal distributions, there's actually other distributions. There's other types of distributions. There's a rectangular distribution. There's a skewed distribution. But the ones we're most interested in for our purposes here, as we said, is this normal distribution, which is characterized by a central location dividing our data into two sets. And then the height of the curve is driven by, basically the rise really of the standard deviation will tell us really what's the spread. So if I have a small standard deviation, what that would mean is I have a curve that kind of goes up, kind of narrower, taller, versus a wider standard distribution, which is flatter and more distributed, more spread out. All right. So we can do stuff with this, as we're looking at this. Let's take a quick look at this at our the formula around this. So this is the formula we use for the probability density function. Fairly sophisticated. So basically, but it's using a lot of the same things we've seen before. So we've seen this deviation from off of the mean, all right, divided by the standard deviation. Kind of, we're taking the square root. In this case, what we do is we're actually going to combine pi, which is 3.14, actually 3.14159, and more. And then we also have using e, which is a mathematical constant. These are the values we put in. We're going to punch in as fixed values into our formula here. We're going to combine that with our population mean, expected value, and the population standard deviation. And then x is our, whatever value we want for the continuous variable. All right. Now, one of the tricks we use, or we can use within this standard distribution, since it is a standard distribution, we can actually change the notations. There's an approach in which what we'll do is we'll take the standard deviation and mean, and what we'll do is we'll make an adjustment into something we call standardized normal distribution, which is a z, what we'll call in this case z values. Right? So all the z values means is we're not changing the shape of the curve. All right. All we're doing is changing some of the relative numbers. All right. So the height of the curve remains the same. The width of the curve stays the same. All we're doing is we're going to change the mean to 0. And change this and make the standard deviation 1. All right, so it'll still be there, but it'll be converted to what we call these z units. So the formula to do that is we take the z, where we take the subtract. We take x. The way we convert x to the z is we take x, subtracting it from the mean, dividing it by the standard deviation. Right, and it creates something called a z value. And the z value always has a mean of 0, and it has a distribution of -1, +1. All right, so in this case, we'll use an example. So we have a normal distribution, mean of 100, standard deviation of 50. All right, so what we'll do is we'll convert this. If we have an x value of 200, what we would do is we would then say 200 minus the mean, right, divided by the standard deviation, which is 2.0. All right, so in this case, 200 is 2 standard deviations above the mean of 100. It's kind of how you would translate this to be. All right. And what we can do is now the other thing we can do with this is, because of the nature of our curve here, or our normal distribution, because of the nature of this, we can develop estimates of the probability. We can use this to develop the z value to calculate out the probabilities. All right. So what there's actually a table that has already been calculated for us. It's called the cumulative standardized normal table. Right? And what it does is it gives us, the probability, less than a desired value of z. All right. So let's look how that might work. All right. So this is right here is, for a 0, 2 standard deviations. This would be everything to the left of this is 0.9772. All right, and then the inverse of that would be what is in this tail, all right, which would be 0.2 something. All right. How do we use this? Okay. So what happens is when we do the calculation, what we will do is we have a row and a column for this. All right. So in this case, we're saying the z value is 2.0. All right. So what we'll do is we look at the table. We'll actually go into the table, and to the first decimal point, we will use that to identify the row. All right. And then the column gives us the value to the second decimal point. All right. So in this case, what we're going to do is there's actually this table, which is called the appendix. You can find it in the book, appendix table E.2. We will take, we'll look up in the table for 2 and 0. And what that gives us the 9772. And the table has all of the calculations based on, all these combinations of things. So we don't have to go through the whole, an extensive calculation. All we do is we generate the z value, divide it into its, the component parts, and then do a lookup in the table to find that. All right, so the procedure is, so just kind of do a quick recap of our procedure here, is to find the probability of x between a and b, assuming we're using a normal distribution. Step 1, we draw the curve in terms of x. Step 2 is we take the x values, we translate them into z values. And step 3 is we look it up in the table. All right, so the amount of calculation we have to do is fairly simple. We're just doing this x to z value and then looking up, and that's already been pre-calculated in the table for us. All right, so let's take another example here. All right, so we'll say x is the amount of time it takes to download an image file from the internet. It's just kind of a practical thing, and we say our x is a standard distribution or normal distribution. The mean is 18. Standard deviation is 5. All right. So in this case, what we want to do is, if we are saying what's the probability that x is less than 18.6. So 18.6 is just simply a number we're picking out. We're trying to estimate what the speed is. So we're saying, okay, what is the probability that it's going to be less than that, less than 18.6? All right. So what we will do is we will calculate a z value. All right. So x minus the mean divided by the standard deviation is 18.6. All right. That's our value. That's the value we're looking for. The mean is 18.0. Divide that by 5.0 is 0.12. All right. So we have an x value. Simply convert that to a z value. So we go from mean of 18, standard deviation of 5, to a mean of 0, standard deviation of 1. All right. And then we look it up. All right, so in this case, what we're going to do is 0.12. All right, so what we'll do is we'll look at the table, the z table. So we'll find the 0.1 on the row. We'll find the 0.02 in the column. So the answer is 5478, 0.5478. All right, so we can do this. So we can do this calculation very quickly using the tables, because a lot of the heavy lifting has already been done. Heavy lifting is already in the tables. All right. And we can use this to find, like what we call here the upper tail probabilities. Do a similar thing. So what we'll do is we'll take our uh, normal distribution, mean of 18, standard deviation of 5. And what we'll do is we want to estimate the probability that x is going to be greater than. So that was basically what we were looking at previous. We were looking everything to the left. Now what we want to do is we want to look at everything to the right. So if it's greater than 18.6, what's the probability that something is greater than 18.6? Once again, we do the same. We'll do this. We'll do our same calculation. All right. Except in this case, what we will do is we'll calculate, our value of 5478. We just simply subtract it from 1, which means it's 4522. All right, because don't forget, everything adds up under the normal distribution to be 1. All right, 0 is our expected value or median or the mean, and 50% on either side. All right, so if I calculate the one value, if I simply subtract it from 1, I will get the other value. I can estimate the other side. All right, so the steps, to find the x value of a known probability. Step 1, you find the z value, and then we convert the x units. We convert it to x units. All right, so if we know the z value, if we know the probability, we can also reverse this and find the x value as well. All right, so in that case, what it would be is we would take the mean plus the z value times the standard deviation, which will give us our x value. So we want to figure out what's our number on the curve. And then find the x value for a known probability. Once again, assuming normal distribution, mean of 18, standard deviation 5. Find x such that 20% of the download times are less than x. All right, so we know that we want 20% of the download times to be less than x. All we want to do is we want to calculate the x value, given that we know what the probability is. So in this case, what we will do is we will use our table, so it'll be 0.84 is what we will calculate. All right, once we find that, and that will translate to a 0.00, excuse me, a 2.2005. Okay, which will translate to a negative 0.84, which is the 20%. All right, so this is a 20%. So you read this. This is the 20% probability. So it's a 20%, which is technically, it's 20, 05 is the it's the 20%, and it's 0.84 is our z value. Okay, so that makes sense. So it's the same. We can do variations of this. If we know what the z value is, we can calculate the probabilities. If we know what the probabilities are, we can calculate the x. So we can calculate all these things, but it centers around using both the standard distribution, in addition using the standardized normal probability table, which always has this stuff in it. So it's simply a matter of separating our number into a row and a column and seeing what the value is. Okay? So I can also convert the x units using the formula. So the mean is 18. The z-value is minus 0.84. Actually, that's a negative 0.84. Negative 0.0804. Times 5, which is 13.8, which is our x value. So what that will translate to is 20% of the values of a distribution with a mean of 18.0 and standard deviation 50 are less than 13.8. Right. And that really is a summary of chapters 4, 5, and 6.